So after this little insert on invertibility, injectivity, operators being bounded from below, we are now all set for our next section, which is about the finite section method and sufficient condition for its applicability. Let's call it positive definiteness and rectangular finite sections. Well, we will see what's coming. Let's start with positive definiteness. Recall this from your linear algebra course where dimensions were finite. So there we called an operator A from x to x positive definite if A is self-adjoint, so it equals its adjoint operator, and if the scalar product, which is the standard scalar product in your space X, which is usually R to the n or C to the n in linear algebra, of A times a vector X with the same vector X is always positive, no matter what vector X you try. And the only exception is, of course, the vector X equals 0, because then clearly you get 0 here and 0 here. So this would be equal to 0 then. Okay, so looking at this, our space X should be a Euclidean space, because we obviously need a scalar product in X. But it could be real or complex, and then it is noteworthy that this expression always seems to be real, because otherwise we couldn't compare it to 0 on a greater than or less than or equal to basis. Try to convince yourself that indeed this is always true. Okay, well, because this expression here is not very handy, we quickly came up with other characterizations of the word positive definite for n by n matrices, and one of them has to do with eigenvalues. Let's quickly see how this expression here is connected to eigenvalues and eigenvectors. So if x is such that ax is a multiple of x, let's call it lambda x. Well, of course, this is an eigenvector, eigenvalue constellation here. And if, for simplicity, the norm of our eigenvector x is 1, well, we know that we can scale eigenvectors as we like. They remain eigenvectors. Then, looking at that expression, we can observe the following. Okay, so let's replace ax by lambda x, then get the lambda out, and then note that this here is the norm of x squared, which is 1 by our assumption. We can see that this expression is exactly returning us the eigenvalue lambda, and the condition that we find here implies that all our eigenvalues have to be positive. In fact, this also works in the other direction. So if A is self-adjoint and all its eigenvalues are positive, then it's positive definite. I'm sure you remember that from your linear algebra course. In particular, one can show that the best lower bound on this scalar product, when x is restricted to vectors of norm 1, is exactly the smallest eigenvalue of your matrix A. And indeed, it is assumed if you insert x equal to the corresponding eigenvector here, so that this infimum is in fact a minimum. And to show this, you have to plug in arbitrary vectors x here, expand them in a basis of eigenvectors, which you always can do because you're diagonalizable by self-adjointness. Okay, and then play around with the coefficients and you will see when you reach the minimum and the maximum. Okay, and like we concluded earlier, all eigenvalues are positive, and of course that includes our smallest eigenvalue. So you get a positive number here. And now let's come to the general setting. So now your Euclidean space X could have infinite dimension if you want. Then here's our definition for positive definiteness. Our operator A from X to X is positive definite if it is self-adjoint, and if this condition here holds, if the infimum of our scalar product, where we restrict consideration to x's with norm equals 1, is positive. In case you're also allowing equality here, then you speak of positive semi-definite operators. And here's a little lemma. Let A be positive definite. Then statement A, the scalar product of ax, x, is greater than or equal to little c times norm x squared. And this holds for all little x's in our space X, where little c is the infimum that we're talking about here in the definition. Okay, so by the definition, we get that the scalar product ax, x is always greater than or equal to its infimum with this little c, but that's only when you restrict consideration to vectors x of length 1. Now this is what happens when you allow arbitrary lengths. You have to multiply by that length squared here next to the c. Okay, and this is easy to see. Let's start with this proof before we state statement B. So if x is not the null vector, then you can just follow the simple computation here. You just rewrite x as follows. You just divide by norm x and then you multiply by norm x, and the same here. But now it's clear that you can get this scalar here in front of your operator A, and from here you can get it in front of your scalar product. But also from here the other scalar you can get in front of your scalar product. In case of a complex scalar product, you get the complex conjugate in front, but this is obviously real here. Okay, so you end up with this expression, but now this here is the same vector that has norm 1. So it's one of these vectors here for which you have tried the infimum, and the infimum turned out to be little c, so we can bound this expression by little c. And that proves our claim for the case when x is not the null vector. But looking at this separately, we can immediately tick this case also. Okay, so you get 0 here, 0 here, so you get 0 on the left, and some constant times 0 less than equal, yes, is true. Which finishes the proof of part A. And here is statement B. So again, let's read from the top. A is a positive definite operator, then, and now we claim that A is invertible. So let's prove B. So by statement A, we have this. And because this scalar product here is always real and positive, we can write modulus signs around. And now use Cauchy-Schwarz. And then divide by norm x. And here's what you get. Okay, so we see that our operator A is bounded from below, and the little c here is playing exactly the same role as it did in our lemma 8, where we introduced this property. So by that same lemma 8, A is injective and has a closed image. But when we say positive definite, then we always assume that A equals A adjoint. So of course we should also use that. So then also A adjoint is injective because it's the same as A. Okay, but taking these three properties together by lemma 7, we get invertibility of A. And this finishes the proof also of part B. Maybe you're wondering why the proof of B was not easier, because we've been speaking about eigenvalues before, and we said positive definite means all eigenvalues are positive, so no eigenvalue can be 0, so A must be invertible. Well, now we are infinite dimensional, and in this infinite dimensional setting there could be spectral values that are no eigenvalues, and as soon as one of them is 0, then A is not invertible. And but at least from what we saw before, it's not so easy to exclude that possibility, so we did have to write down a slightly longer proof, but I mean it's not really long, because we of course had these powerful results lemma 8 and lemma 7 in the back of our heads already.